Welcome to a new video in a series on modular forms, and this video will be a discussion on the definition of modular forms. So in the previous two videos, we've introduced elliptic functions, and one important example of elliptic functions was the Weierstrass function, where we discussed its expansion, and we claimed that its coefficients are actually modular forms of even weights, but we haven't actually defined rigorously what a modular form is. So this video is going to go over the definition, and we're going to briefly discuss why the Eisenstein series appearing in the expansion of the Weierstrass function are modular forms of even weight. Let's recall the setup. So we're interested in functions defined on the upper half plane. And I remind you that one of the reasons we got interested in modular forms is that we initially asked the question of what kind of analytic functions would satisfy the equation a tau plus b over c tau plus d equals to f of tau, where tau is in the upper half plane. So we've discussed that constructing such functions would be hard to begin with. So what we said is that instead of constructing such a function, what we're gonna do is that we're gonna construct two functions that satisfy equation the functional equation f of a tau plus b over c tau plus d equals to c tau plus d to the k f of tau, and so that if we can construct two such functions where k is the weight of the function, if we can construct two such functions, one of which is non-zero everywhere, we can divide two such functions and get a modular function. So function satisfying this functional equation and a growth condition are called modular functions, and these are things that we're interested in. And I remind you that the coefficients a, b, c, d are coming from the group SL2Z, which we discussed in the previous video. These are made 2 by 2 matrices with determinant equal to +1 and coefficients that are integers. And this brought us to the discussion of modular forms. So let us define in a more rigorous way what a modular form is. So here's the definition. So a modular form of weight k is a function f that is it is a complex function that is analytic on the upper half plane, and it satisfies the functional equation that we've just talked about, and k, I remind you, is the weight. So we take any matrix in SL2Z, and we require the function to satisfy this functional equation. And in addition, we require the function to satisfy a growth condition, and this growth condition can be summarized by saying that we want the function f to be bounded as tau goes to I infinity, as tau goes to infinity in the imaginary. I infinity, okay. So and this is the growth condition that we're talking about. Now, one interesting thing about modular functions is that if you look at the first condition, you see that the function satisfies the equation f of tau plus 1 is equals to f of tau, meaning it's one periodic. So the function is one periodic, and it's nice enough, thus it admits Fourier expansion of this form. So we can write f of tau as the sum of a n q to the n, where q is 2 pi I tau, And this is sometimes called the Q series or the Q expansion of a modular form. So you notice that as tau goes to I infinity, there is a problem here, because when you send tau to I infinity, there's a problem when n is negative. However, we require the function to be meomorphic at I infinity, in the sense that the pole is the pole is of finite order. So let us repeat briefly what we just said. So a modular form is a complex function that is analytic on the upper half plane, and it satisfies the functional equation f of a tau plus b over c tau plus d equals to c tau plus d to the k f of tau, and it's bounded as tau goes to I infinity. Now a special class of modular forms are what's so-called cusp modular forms, and these are the functions that vanish at I infinity. So if you look at this expansion, if m is bigger than or equal to 0, then there's no problem when q is 0, which is equivalent to sending tau to I infinity. Alright, so this is one way to define modular forms. However, there is also another interesting way to define modular forms, and it might give you an intuition of why these functions are interesting. So there's an equivalent way of defining what a modular form is, which is as a function of lattices. So we may define a modular form as a function of lattices in the complex plane. So let me elaborate on that. So an equivalent way of defining what a modular form is that you define it as a function that is defined on the set of lattices. So you consider S to be, so you define S to be the set of all lattices in C. For example, we consider all lattices of the form omega 1 Z plus omega 2 Z. And in this case, we call this lattice to be a lattice generated by omega 1 and omega 2. Anyways, so we define it as a function on the set of lattices that is complex valued, but we require a similar functional equation to be satisfied by this function. In other words, we require that if we have a lattice and we scale it by a non-zero complex number, we require the function to satisfy a similar functional equation, in the sense that we require it to pull that constant outside with a power of minus k. And now, to see why this definition of modular form is equivalent to the first definition that we gave, I'm gonna construct an isomorphism between the space of modular forms of weight k and the space of functions of lattices. So we consider all the functions of lattices and we collect them in a space, and we have the function of modular forms, and we're gonna claim that these two spaces are actually isomorphic. So it's easy to see this via the map. I'm gonna call it gamma. So the map is that, so if you call this mk the space of modular forms, and this is the space of functions of lattices, if you start with a modular form, you can get a function of lattices that maps a lattice to the value, to the complex number omega 2 inverse f of omega 2 over omega 1. And to see why this function is an isomorphism, the easiest way is to construct the inverse of it. If you start with a function of lattices, so this function is defined on the set of lattices and it's complex valued. You send this, like the inverse is defined by sending a function of lattices to the function f of tau that is defined as f of tau equals to f of the lattice z plus tau z. So in other words, you take the lattice generated by 1 and tau. So now it's an easy task. Like when you compose these two functions, you will see that this is actually the identity. So this justifies the equivalent way of defining a modular form as a function of lattices. So you may wonder that there are some properties of a modular form that we defined in the original definition that aren't appearing here, or there's no equivalent property of them here. Well, you're right, because I skipped these. You require similar things. For example, you require this function of lattices to satisfy the property that if you take f of tau and define it to be f of z plus tau z, you want this to be analytic. You want this to be an analytic function of tau. And if you take the absolute value of, so if you take a lattice and you take an absolute value of this, you want this to be bounded when this lattice have points that are away from zero. So you want the smallest non-zero element of this lattice to be bounded away from zero. So these are the equivalent properties that we forced the modular form to satisfy. And I did all of this video to discuss why the Eisenstein series that we defined in the previous video are actually modular forms. So let us discuss this briefly. So I remind you, we fixed an integer strictly bigger than 2, and we defined the gk of tau to be the sum of 1 over m plus n tau to the k, as m and n run over all the integers, but we require m and n not to be 0 at the same time. So we proved that as long as k is strictly bigger than 2, this function is nice, and they come up naturally as coefficients of the expansion of the Weierstrass P function. You may refer to the previous video to see this. So this function is actually a modular form if k is even. And to see this, you just need to observe that if you have gk of a tau plus b over c tau plus d, and you have a, b, c, d is in SL2z, then you just need to notice that if you recombine terms here, what you will get is c tau plus d. If you take a common denominator, if you replace tau by a tau plus b over c tau plus d, and you make a common denominator, this is gonna be a sum of 1 over something like am plus cn tau plus bm plus dn, something like that. And you'll be running over all the integer, over all mn in z squared except for the 0 term. And it's clear that you're covering z squared again, so this is just literally gk of tau. So this justifies why this function is a modular form. And I want to also briefly discuss the equivalent way of defining this function, because we discussed an equivalent way of defining a modular form. So equivalently, you may define this as a function of lattices. So you take a lattice L, and so this is a function of lattices. It takes a lattice, and what does it do to it? Well, it sums over all the elements of the lattice that are in L, say lambda in L. Of course, you take the non-zero ones, and you sum 1 over lambda to the k. So in this way, we can define this modular form as a function of lattices instead of defining it as a complex function. And one interesting property that we're gonna dwell on in the coming videos is that we proved that SL2Z is generated by the two generators s equals to 0, -1, 1, 0, and t equals to 1, 1, 0, 1. So SL2Z is generated by these. So for example, we study what happens by the inversion. So we study the inversion property of the modular form due to S. So this is just S times tau. And this is going to be tau to the k gk of tau. And the other property is called the translation, which is gk of tau plus 1 equals to gk of tau. And this is called the translation property. And since these generate SL2Z, the condition in the definition of modular forms, the modularity condition, the condition that the function should satisfy the functional equation of this form, is equivalent to the function satisfying these two equations.